Hello, my name is Hong Xu. I'm a product engineer on Rust team in Esri development. In this presentation, I'm going to demonstrate the capabilities of change detection in ArcGIS. I'll start with an overview of the change detection capabilities and then demonstrate three use cases. First, we'll use European Space Agency's land cover data to explore the land cover changes in Amazon basin. In the second demo, we'll analyze timber harvest pattern in West Cascades Forest using landcover. Landcover here is a new change detection algorithm which we have just added in Pro 2.7. In the third demo, I'll show how to monitor forest disturbances from Landsat time series imagery using CCDC algorithm. Detecting change using two images over the same area taken at different times is a classical image analysis capability, comparing the pixel value change or classifying each image first and then comparing the class change between the two. So with this simple approach, we can find out what the changes are and where the changes are. As the advance of sensor technologies, we now have access to a lot of images. We have free access to the whole Landsat image archive. So detecting changes from time series imagery and understanding the cause and patterns become very important. With time series imagery, you can detect many types of changes, gradual change and abrupt change. The gradual changes are forest infestation, land degradation, or forest recovery. The abrupt changes are things like wildfire, deforestation, and urban development, and so on. ArcGIS offers change detection capabilities for both two-image change detection and time series change detection. Pro 2.7 has a new change detection wizard, which allows you to perform typical change detection workflows. Land cover change detection, pixel value change detection, and change detection from time series imagery. ArcGIS also provides tools, functions, and APIs that allow you to perform change detection with Python. For two-image change detection, we have compute change raster tool or compute change function. It's a Rust function. For time series imagery, we support CCDC and landcover algorithms, which I'll get to that in a bit. The summarized categorical raster tool worked with categorical time series data like land cover data. It is a new tool in Pro 2.7, which you will see it in demo. These are geoprocessing tools, and there are also corresponding service tools and functions for enterprise. So you can use either ArcPy and the geoprocessing tools to process data locally, or use ArcGIS API for Python to work with the web layers, with service tools, with your enterprise. One of the time series change detection algorithms we support in ArcGIS is CCDC, continuous change detection and classification. This algorithm uses an harmonic regression model to detect the change. So it needs a lot of images because it requires a dense pixel time series to construct a harmonic model. The model output is also a time series, which we call it a change analysis raster, where each raster in the output is a multi-band that contains model coefficients. In original time series data, the pixel values like trees are different in different seasons. However, the pixel values in the model output, which are the model coefficients, are same across times as long as it is within one model. The harmonic model takes account of the seasonality. So the output change analysis raster can be a good resource for classifying time series imagery. If one pixel time series cannot be modeled with one harmonic function, then the model breaks, and the date at which it breaks becomes the change date. So we can extract the earliest change, latest change, and the largest change. The other algorithm is landtrunder. Its full name is Landsat-based detection of trends in disturbance and recovery. So the name kind of tells what the goals of the algorithm. This algorithm uses one image per year and performs temporal segmentation for each pixel time series. So each segment has a start date and an ending date, and it also has the magnitude and the duration. So these properties can be used to extract more information of the changes, like gradual change, gradual decrease, slow decrease, or slow recovery. The output is also a change analysis raster where it stores the linear regression model coefficients instead of a harmonic regression model. This is the time series change detection workflow. So from your input images, prepare a multidimensional raster. It can be either a multidimensional mosaic dataset or a multidimensional CRF. So we will not get to that in this demo theater, but the URL in the slide links to a blog with the steps on how to create. So once you have a multidimensional raster, then use either the detect change using CCDC tool or detect change using the landtrunder tool to create a change analysis raster. So which tool to use really depends on the availability of your image and also your applications. And from change analysis raster, we can do two things. First, to use the detect change from change analysis raster tool to create change maps. The second is to classify time series image using image classification tools. The training tools and the classify tools have all been enhanced to support time. So this finished the brief overview of ArcGIS change detection capabilities. And next, I'm going to use 3 use cases to demonstrate the capabilities. In the first demo, we will analyze land cover change using ESA land cover time series data. The European Space Agency's land cover data is yearly global data from 1992 to 2018. And I had created a mosaic dataset as the input for this demo. The yellow box is our study area, which is in Amazon basin along Amazon rivers. In this demo, I'm using ArcPy and ArcGIS notebooks because I can switch easily to map view to visualize the result. To start, I import ArcPy, check out image analyst extension, as some functions require image analyst, and also using environment setting to define my study area, which is the extent of the yellow box. And first, I create a raster object from the input using arcpy.raster. And because the input is a multidimensional raster, time series data, so I set the second option to be true, and then use variables properties to get the variable name and dimension name in the data. You can see that the dimension name is SDD time with 27 images. 27 years land cover data. And I can also get the dimension values using this get dimension value properties. These are the years of the land cover data. So next, to look at the land cover changes over time, I use the new summarize categorical raster tool to compute a class summary table. This tool calculates the class counts for each class at each time. So the output is like this. The fields are class name, and values in the cell are the pixel counts for each class at each year. And here we have the dimension field with dimension values that is from the input raster. So with that, I can use ArcPy chart to visualize the trend. For example, I'm interested in evergreen tree class. I can create a chart with that field. You can see the trend easily. The evergreen tree cover decreases greatly each year, but slows down in 2004, and it becomes stable afterwards. With the same input table, I can look at other classes. This chart highlights the patterns of crop and vegetation land cover trend. And these two classes increased steadily till 2004, same year. So it is very possible that the evergreen tree were cut and converted to crop and vegetation land. So to quantify that, I'm going to compute the change. To do so, I use subset function to get the land cover for 2 years. And one is from year 1992, and one is from 2018. So I simply call subset function with dimension values. Because I need to use class name, so I use Raster RAT property to get the raster attribute table and list the class names. Then I can call compute change raster tool, where I set from to raster and also define the from class to be evergreen tree cover and the deciduous tree cover. Set the to class to be an empty string, which means all classes, and then compute to get the change raster. Save the result as a TIFF file. So this is the display of the change raster. And we can switch to map and overlay the result on top of base map layer. And now you can see the distribution of these changes. The changes are mostly along Amazon rivers. And I can see the change categories in the table of content. These are labeled from class to classes. The raster attribute table contains the change classes as well as the counts, pixel count, or areas of the change. So you can select any change category that you are interested in to visualize. This chart shows all the classes converted from evergreen trees, and the majorities are converted to crops and vegetations. So this is how you can analyze land cover time series data to look at the changes using ArcGIS. In the second demo, we want to analyze timber harvest pattern using land trender algorithm. The study area is in Western Cascades Forest, a large commercial timber production area in Oregon State. We want to understand the spatial and the temporal patterns of the timber harvest over that area. The input time series data is Landsat imagery of summer season from 1984 to 2020. And I had created a multidimensional raster from the time series data as the input. In the first step, we will create a normalized burn ratio raster because it is effective in detecting forest disturbances. Then we'll do land trend analysis to generate a change analysis raster. And from there, we'll create logging disturbance map, recovery map, and also classify the whole time series imagery. This demo, I'm using ArcGIS and Jupyter Notebooks. And same as before, I import ArcGIS, and I also import all functions in the arcgis.ra. This is the image analysis module that has all the image analysis functions. And also define environment setting for parallel processing and workspace, output workspace. The first step is to create a raster from the input using arcgis.raster. And this raster has 80 slices. And this is the display of the multidimensional raster. The second step is to create an NBR raster using the NBR function by giving the shortwave band, infrared band, and then use a render function to display with a color ramp. The third step is to perform land trend analysis. And here I use analyze change using land trender tools to generate a change analysis raster. The input here you see that is the NBR raster we just calculated. And here I define a snapping date. This allows the algorithm to choose a good pixel if there are multiple images within a year. Having multiple images for a year can reduce the possibility of getting no data in the output. I also define maximum segments to be 5. This will reduce the noises and avoid subtle changes. And take the default for the rest, process, and save the process result. As you can see that the output is a multi-dimensional, multi-band raster. And I render the data with the 3-band 135 using RGB render. And the 3 bands are slope, fitted value, and magnitude. So this is the display of the change analysis raster. Next, we'll derive information from the change analysis raster. First, we detect abrupt decrease. Logging is a type of abrupt decrease. I use detect change using change analysis raster GP tool, where I set change direction as decrease, duration is within 4 years, and the magnitude is between 0.4 and above, which is an estimate of the NBR value change from forest to disturbance. Then process and generate disturbance raster. Then display with the color ramp using render function. This is a screenshot that I overlaid the result with the basemap layer, so the patterns can stand out. The pixel values are days, where pixels with yellow light color means change started in early years, and dark pixels means change happened in recent years. The regular square cut pattern is due to forest protection. Left is a state park, where there's no logging, and on the right is protected forest. Some logging happened in early years when protection has not been regulated yet. So many information can be interpreted from this disturbance map. Next, we'll look at the recovery process. How long for these disturbance pixels to recover and become trees? So here's the workflow. We retrieve increasing segments and get the starting days and ending days of the segments. Then do a minus operation to get the number of days, and then convert to years. The code simply call detect change using change analysis raster tool, and to get the from years and ending years, and then do a calculation and get the recovery duration in years. This is the screenshot of the output duration map overlaid with the basemap layer. Pixels are number of years for disturbance pixels to recover to trees. Red means more years and yellow means less years. So the next step is to classify time series imagery to understand the forest change. The input are the change analysis raster generated and training sample collected using Pro Training Sample Manager. I use train random tree classifier tool to train and get a class definition file, ECD file, and then use classify raster tool to classify the time series data with the trained classified definition. This is the classified time series output. It has 4 classes: forest, disturbance, recovery, and slow recovery. Finally, I use summarized categorical raster tool, which I had showed in the first demo, to calculate a class summary table from the output, and create a chart to visualize the forest changes and the forest dynamics. Same demo can be implemented using ArcGIS API for Python. So this is a API for Python notebook. And I include GIS module, GIS.raster, Raster functions, Raster analytics module, create a GIS object using the portal URL and the credentials. I publish the image input data as an image layer in portal. Get the portal item and create a Raster object from the URL, layer URL. Use multidimensional filter to display a single slice and create an NBR raster using NBR function. Then perform land trend analysis using this service tool. So you can see that the workflow is same as in ArcGIS. The APIs are not exactly same, but very similar. The output is an hosted image service in portal, and I can get the portal URL. I then extract band, the first, the third, and the fifth bands, and then display as an RGB. So this is the change analysis raster. For detect abrupt change, I can use the detect change analysis raster service tool and generate the disturbance map and display using a stretch function, then add to map. Same workflow can be done for recovery duration map. For image classification, I need to upload training sample as a feature layer and convert to JSON and call train classifier service tool to generate classification definition. As you can see that this train classifier has support a new parameter dimension value field. And now I can call classify tool to classify the time series data. This is the final result. As you can see, it has 34 slices in the time series. The third demo is monitoring forest disturbances using CCDC method. Because CCDC worked with more data in final temporal resolution, it can detect which date a change had occurred, or land trend detects which year. So CCDC can be used to monitor forest disturbances. The study area is in the west of Yosemite National Park. The data we have for this area is 267 Landsat images from 2013 to 2020. And I had created a multidimensional raster out of this collection. The diagram outlines the workflow. We take time series image as input, perform CCDC analysis to generate a change analysis raster, and detect the change date, find the images before the date and after the date, and quantify the change. We use ArcGIS API for Python to demonstrate this workflow. So we begin with importing ArcGIS module, importing Raster module, Raster functions, Raster analytics modules. And this is my portal URL. And I had published my data as an image service to that portal. I create a GIS object from portal URL and credentials, get a layer from my service, and create a Raster object from the layer URL. Using variable properties, we can see that this is a multidimensional raster that has 267 images. We use multidimensional filter function to get the first slice to display. Now we have a multidimensional raster ready and ready to perform a CCDC analysis. We use analyze change using CCDC service tool to generate a change analysis raster. The output is a portal item, so we get the layer from the item and display with a stretch function. By default, it displays the first band, which is the slope band. Next, we use detect change from change analysis raster service tool to detect the latest change. And again, we get a layer from the item and display with the color map function. The pixel values in the output are dates. Red pixels are recent change, and the green pixels means early changes. I'm interested in the change in those red pixels and find the value is October the 6th, 2019. We can explore what had happened around that time using the temporal profile of the change analysis raster. To do that, I use a smaller window from September to November because the whole time series is too long to display in one graph. And here is the temporal profile of the regression slope at this location. We see a sudden drop at this time, October the 6th, and this indicates a forest disturbance. To find out what are the changes, I use multidimensional filter function to select images before and after the change. This is the image in October the 3rd, 2019, which displays normal. The next image is October the 11th, is during the change. The white strips are no data pixels caused by the well-known Landsat 7 sensor failure. So this is the Landsat 7 image, but we still can see smokes in this area. This is an image one day after. It's a Landsat 8 image. We can see burn scars clearly. And this is the image on November the 4th. Fire are completely contained, but we still can see scars, burn scars. We did some research and find out this is the Briceburg fire started on October the 6th. To quantify the change, we calculate NDVI for the images before and after fire and compute a change raster using computer change function. We use remap function to remap the pixel values to 0 and 1, where 1 means burned pixels, and save the result as a total item. Add the item to a web map to display. Further, we can calculate the areas that are affected by the fire. To do so, I define an extent and calculate the pixel histogram, and add all pixels with value 1 together to get the total count of burned pixels, and then time pixel area and get total area of burned pixels. So the fire has consumed 4,045 acres. So this is an example of using CCDC and Landsat images to monitor forest disturbances. Now we have finished our 3 demos, and here are some more resources for you. I used the multidimensional raster a lot in the demo. So if you want to learn more, you can attend the workshop working with multidimensional data in ArcGIS. You can learn more multidimensional raster analysis by checking out this demo theater, predict and trend analysis of raster data. If you are interested in extending raster capabilities, there's a session on advanced custom raster processing using Python. Okay, with that, I hope you enjoy this presentation. And please provide your feedback for this session by clicking on the session survey link below the video. And thank you for watching.